Right, I'd like to give you just a very brief overview of the autonomic nervous system before we transition into the endocrine system. So, autonomic nervous system, endocrine systems are going to be major players in regulation. That's one of the things we want to understand here. What I'm comparing here is the somatic nervous system over here on the left side to the autonomic nervous system over on the right. And the somatic nervous system really only innervates skeletal muscle. So this is involved in voluntary movement. Whereas the autonomic nervous system is, well, autonomic. This is usually unconscious, so we don't normally have voluntary control over much of the autonomic nervous system. There are some exceptions, especially people who practice yoga have some control over the autonomic nervous system, and we do have some conscious control on some autonomic processes even without that practice, like the respiratory system, for example. You can consciously control that if you want to. So voluntary, I'm going to say mostly involuntary. Because it's automatic, right? That's why we call this the autonomic nervous system. Now, you don't really have to memorize anything about the somatic nervous system. I'm just using it as a point of comparison here for the autonomic nervous system. So you can see the cell bodies here in the somatic are in the central nervous system, and they send their axons out to the target, and it's skeletal muscle. That's it. Now, the autonomic nervous system, we do have cell bodies in the central nervous system, but they synapse on another cell out here. And we have clusters of these cells together in a cluster of cells in the peripheral nervous system outside of the CNS. That's called a ganglion. Or ganglia is the plural if you have multiple. If we had that collection of cell bodies in the brain somewhere, we would call that a nucleus. So just a little bit of terminology on clusters of cell bodies. These do have some connective tissue around the outside and some specialized glia associated with them too. But then we have the axon that goes out to the target tissue. And notice there's no skeletal muscle here. The autonomic nervous system does not innervate skeletal muscle. It can indirectly affect muscle tone, but that's through a complex circuit up in the midbrain. So let's look at some of the targets. Well, smooth muscle around the bronchi, for example. We can control bronchodilation. Smooth muscle in the vasculature. We can control the tone or the diameter of those blood vessels, and that'll become important in the cardiovascular system. Glands. Well, there's the endocrine system right there, right? So the autonomic nervous system can have an influence on the endocrine system also. Cardiac muscle is another target, and adipose tissue, fat. And I'll tell you just briefly a little bit about how that works in general. So we have a slightly more complex system here, more synapses. So this, I did want to tell you, is these axons are myelinated. And actually, so are these. So these are also myelinated. But these tend to be unmyelinated. And I keep saying these and these. I should give you some names for these too. Whenever we see a collection of axons together, in the peripheral nervous system, we'll call them a nerve if they have the associated connective tissue around them, the perineurium and all that. Well, they also look fibrous if you dissect them apart. So we tend to call these fibers for that reason. So this one is before the ganglion. So the one before the ganglion is called preganglionic. So that's a preganglionic fiber there. And then postganglionic is that unmyelinated fiber right there. So that's postganglionic. And you may have gotten this in your intro classes as something else to memorize, but there are some important characteristics to the preganglionic and postganglionic systems that we need to understand because it's important functionally. And we'll get to that shortly. I want to give you just a brief overview, probably at a level that you may already know in comparing and contrasting sympathetic versus parasympathetic branches of the autonomic nervous system. You've probably heard the sympathetic branch called the fight or flight. I'm going to put quotes around that because that's not necessarily correct. And over here you may have heard the parasympathetic as rest and digest. Also with quotes around it, because we need to understand the distinctions here. So whenever people talk about fight or flight activation in the sympathetic nervous system, well, that's maximum activation, like you see in this guy. That looks like panic attack to me, but full-blown activation of the sympathetic nervous system. Well, we have full range. There can be a small amount of activation all the way up to this full activation. And that's true of the parasympathetic nervous system too. Slight activation all the way up to maximal. So these two branches of the autonomic nervous system, these are not mutually exclusive. As a matter of fact, I'll talk a little bit later about a lot of organ systems are innervated by both the sympathetic and the parasympathetic nervous systems. And we call that dual innervation because they're receiving inputs from both of these branches. You can think of it a little bit like having an accelerator and a brake on the system. So that gives you a wide range of control. So that's a very useful thing to have. So some other generalizations here with sympathetic versus parasympathetic nervous system. Usually in terms of the effects, they're usually fairly diffuse. So they activate a wide range of systems simultaneously, and they tend to be longer acting than the parasympathetic. So I'm going to say longer. Longer lasting, how about? And over here, this is more discrete. So comparing that to being diffuse, I'm going to say it's discrete. And that's partly based on just the anatomy. I don't really need a space there. Now I don't want to erase it again. But discrete, so focused. How about that? And this tends to be faster, so more rapid. I know it doesn't look like it with Homer sitting on the couch there. And the effects tend to be fairly short-lasting. And that has to do with the neurotransmitters and how these things are wired up. So we'll discuss those in a little bit more detail. Again, remember, it's not either or. We usually have these things working with each other. Both branches of the autonomic nervous system are working together. I would add one more thing here in terms of the functionality. So sympathetic nervous system tends to liberate energy from storage. So I'm going to call that catabolic, because it's breaking down energy stores. Yeah, and you might guess this is the opposite. This is going to be more energy storage. So that would be anabolic. And just in very general terms, we'll talk about stress in a lot more detail when we tie the autonomic nervous system in with the endocrine system. But I think it's pretty obvious. Stress that's chronically activated can be detrimental, right? There's only so much catabolism you can do before you start depleting stores and also start doing serious wear and tear on the nervous system. And right, you can't live like this all the time either. We have to free up some of those energy stores, otherwise you just keep storing more and more and more, just like Homer there. All right, so a little bit more on the anatomy and the preganglionic fibers and what I was pointing out before. So just in very general terms, again, this is before the ganglion, so we have the axons of the fibers that are where the neurons in the central nervous system, the preganglionic fiber. Remember, these are myelinated. And these postganglionic fibers tend to be non-myelinated, so unmyelinated. And just thinking a little bit about the rate of response I was telling you just a moment ago, the parasympathetic tends to be faster and more discrete. That probably isn't immediately obvious to you, again, with somebody sitting on the couch, until you start thinking about this. Well, this fiber has myelin on it, so what kind of conduction speed do we have here? That's very rapid, isn't it? And then we have this slower conduction speed in the postganglionic fiber. Well, in a parasympathetic nervous system, the ganglion that contains these cell bodies and their dendrites out here, those tend to be very close to the target organ. So we have fast over a long distance, and the slower part is over a shorter distance. So overall, this is faster than the sympathetic, because we have the opposite arrangement here. This ganglion tends to be right next to the vertebrae in the thoracic cavity. So our myelinated fibers tend to be short, so our fast component is over a short distance. And then our postganglionic fiber that goes out to the target organs, that tends to be longer because it has to stretch all the way out to the target, and it's over an unmyelinated fiber, so that'll be slower. So that's why we have this faster conduction here in the parasympathetic nervous system. Not only that, by having the ganglion next to the target, we have really this discrete synapse here, so that's why this is more focused. Now it looks focused here, but here's another reason why the sympathetic nervous system is more diffuse. The adrenal medulla is considered part of the sympathetic nervous system, and it can release epinephrine and norepinephrine into the bloodstream. So that's certainly more diffuse, right? So this is more widespread. And it would take longer. So that's another way to remind yourself that the sympathetic nervous system is going to be slower acting in that regard. Other factors for looking at this anatomy, it tells us that there are really only like 3 neurotransmitters we have to pay attention to here. Acetylcholine, norepinephrine, and epinephrine. And I can tell you right now, the release from this preganglionic neuron into the ganglion, that is always norepinephrine. Or I'm sorry, that is always acetylcholine. Wow, okay, this is always acetylcholine. It doesn't matter which branch we're talking about, it's acetylcholine. And I even know what type of receptor this is going to be on this ganglionic neuron here. This is going to be a nicotinic receptor. And that's one of those ligand-gated sodium channels, so that's excitatory. So we'll always get this excitatory effect. It doesn't matter if it's sympathetic or parasympathetic. If it's in the ganglion, it's going to be acetylcholine, and it's going to be acting on a nicotinic receptor. So just knowing a little bit of anatomy tells you a lot about the function. Now, norepinephrine and epinephrine, well, that's actually going to be here in the sympathetic branch. So at the synapse here, this is usually norepinephrine. And in the blood, that's going to be a combination. I'll tell you a little bit more about that. It's epinephrine primarily and some norepinephrine also. Well, what about the parasympathetic? I'll stick with blue for acetylcholine. It's acetylcholine all the way through. So if I ask you an exam question about a neurotransmitter in the parasympathetic nervous system, acetylcholine is a pretty good guess. There are a few exceptions, but it's usually acetylcholine, and I haven't given you those exceptions. So we'll call that a cholinergic. Cholinergic system. And over here, this is called an adrenergic system, named after the old term for the hormones that are, or the neurotransmitters that are released in the blood, whether it be hormones now. Adrenaline, the adrenal gland, it's all named after the same thing. So we call those adrenergic. And these would be like adrenergic receptors, for example. These would be cholinergic receptors on this target. And I think that's about enough about that general overview. So hopefully you can tie a few things together here. We want to look at, this is the sympathetic nervous system here. So I want to talk about the synapse in this thing, because it's a little strange. So they reminded us here we have myelinated fibers here, the preganglionic fibers that would synapse here. We know that this is going to be acetylcholine being released, right? Because it's in the ganglion, it's binding nicotinic receptors on this ganglionic neuron. If we get an action potential traveling down this unmyelinated axon, whoa, look at these weird things. We have all these little bulges along really the axon. So we don't have those nice, neat little terminals that we had when we were talking about the nervous system before. So we call these varicosities. So see if it's labeled. Oh, there it is. Save me from wasting our time with me writing. So those little bulges are called varicosities, and they act like our synapse. So we get an action potential down here. Calcium comes in. We release the neurotransmitter through exocytosis. So let's say it's norepinephrine, which is what it should be in this arrangement. And what we have down here is smooth muscle. And we'll have a receptor on the smooth muscle that will bind norepinephrine. And we'll talk a little bit about those receptor types. But it'll be an adrenergic receptor. And these receptors are all over the target. So we don't have this nice, neat synapse right on top of receptors. So again, the idea of this being more diffuse, I hope, is really starting to gel with you, and that's why I was telling you about that. Now, the effect on the target depends on the receptor. So the effect here depends on, is it excitatory, is it inhibitory? Again, depends on the receptor. Does the smooth muscle contract or does it relax? Again, I'll go ahead and say on the receptor, because that'll determine the effect on this postsynaptic cell. So we'll come back to this because there are some other things we'll want to understand about this. But we do have this kind of interesting arrangement here. Now, how do we turn this off? I can go ahead and add that at this point. Well, there's a transporter here that's going to take that norepinephrine that was released, pump it back into the cell. So we call this, since that's kind of blurred, it's a norepinephrine transporter. It's usually abbreviated NET, but we probably won't talk about it enough to need that abbreviation for the norepinephrine transporter. All right, so that's going to be part of the uptake. Some of this will just diffuse away, right? See how widespread this is? So some of the norepi just diffuses off, doesn't bind may not bind a receptor. And finally, remember the general synapse physiology that we talked about. There's usually an enzyme out here that also breaks down this norepinephrine. And that enzyme out here is called acetylcholine. Let's see. It's abbreviated COMT. I'll go ahead and write it out once, but then we're going to abbreviate it the rest of the time. And that would be out here in this tissue. So this is where we're going to find our COMT. But that is methyltransferase. See why I balked at writing it out? And of course, the abbreviation for that is COMT. And anytime I refer to this on an exam question, I will give you that abbreviation in parentheses. So if you just remember that as COMT, that is fine with me. There's another enzyme inside of this varicosity that helps break this norepinephrine down so it can be recycled. So I'll go ahead and tell you that too while we're talking about enzymes. And the abbreviation for that is MAO. That's monoamine oxidase. And you've probably heard of MAO inhibitors, for example. That's to prevent some of the breakdown and allows for more use of that norepinephrine, or more release, I should say. Let me give you one more general bit of information about this. So when we were comparing the somatic and the parasympathetic nervous system before, actually let me just go on up to it. Okay, it was further than I thought. If we were to, say, cut this lower motor neuron here, what we would get is flaccid paralysis here. So the muscle would relax because we do have some basal output here, this tone coming out of this system. So we produce this muscle tone, and that's why the muscle becomes flaccid or relaxes when we cut that. Well, we can do the same thing here in the either branch of the autonomic nervous system, and we will shut off activity downstream. But that activity will recover over time. Remember upregulation that we talked about with the guy that had the stellate gangliotomy for his cardiac problem? Well, he regained function because of receptor upregulation. So once again, we have some of these hormones in circulation, and particularly in the sympathetic nervous system, we have epinephrine and norepinephrine. So you will regain function in that system. Over here, we would have to get those axons back together again to recover function. Here we're recovering function by upregulating the receptors and using a stimulus through the circulation. Now that should also tell you something else. If we cut that nerve and we lose some function, we must have tone in both of these systems, right? And I'll recap that when we get to the end. All right, so we talked about the synapse a little bit here, this weird synapse that we have with these varicosities. We should probably talk a little bit about the types of receptors that we have here. Make sure I left enough room. We did. Oh, well, here's receptor types. I put it in here as a reminder. All right, let's start with the sympathetic nervous system. There are really just two classes that we need to be familiar with. So I'm going to say sympathetic. Well, actually, I'll be more specific. I'll say adrenergic. So the types that we have are just alpha. I'll be writing this a lot, so I'm just going to give you a little alpha sign for alpha, and beta, or beta receptors. And there are really just two types of alpha receptors, and we just call those alpha 1 and alpha 2. Beta receptors, there are three kinds. We're really creative here. Beta 1, beta 2, and yeah, beta 3. And I know there are subtypes of all of these, but we don't need that. And I'm just going to give you some really basic information on these receptor types. just so we have again, just a very general idea here of these particular types of neurotransmitters. So these bind epinephrine and norepinephrine. So general characteristics, alpha 1, we're going to say those are excitatory. And you know what? I'm actually going to put a plus for excitatory, so I can save a little bit of space here. I don't think I quite left a lot of room. But it's excitatory on smooth muscle, so it will cause that smooth muscle to contract. In just a couple of places for us to remember, the smooth muscle in the blood vessels, I would say arteries, primarily arterioles, blood vessels to the skin, smooth muscle, and I'm going to say blood vessels to the skin, because that actually fits with the story I told you earlier with the upregulation and the effect on blood flow through the skin. That was mediated through an alpha 1 receptor. That's actually all I was going to say about alpha 1 receptors. I'm going to pick a different color here for alpha 2. Alpha 2 is actually inhibitory. And I'm going to use the minus signs for inhibitory going forward. Where do we find those? They are in the CNS, but we want to simplify this. We're just going to say these are found presynaptically. I'm going to stick with my red pen and see if we can go up here. Oh yeah, this is a good place for it. I've already used up some space here on the norepinephrine transporter, but if the alpha 2s are presynaptic, that means, oh boy, red does not show up, does it? I'm going to draw a little box here. This is going to be an alpha 2. So let's think about that. Norepinephrine is released from the varicosity, and it's norepinephrine here is yellow, so it's being released out here into this space. Well, if this accumulates enough, it will start binding the alpha 2 receptor, and that's inhibitory. So that will inhibit further release of the neurotransmitter. See the negative feedback there? So we have a way of regulating how much neurotransmitter is released by having this presynaptic receptor that inhibits further release. Again, nice little negative feedback loop there. All right. Beta 1s. Okay. Those are going to be excitatory. So I'm just going to put a plus sign there for those. Where do we find them? Heart. So if we activate beta 1s, we increase heart rate. We'll probably increase how fast it contracts and how strong it contracts. We'll get to more of that in when we get to the cardiovascular system. I'll stick with red for inhibitory. Actually, yeah, most of the places we're going to talk about, those are inhibitory. I would say this is going to be in places like the bronchi. So let's think about that. If we activate a beta 2 receptor around a bronchus, the smooth muscle will relax, so we get bronchodilation with beta 2 activation. If any of you guys use inhalers like albuterol, well, it's acting on this receptor to bronchodilate, and that's why it's a rescue inhaler. It's going to help you to breathe if those bronchi are constricted. It also will relax smooth muscle, so I'm just going to say vasodilation. In blood vessels that supply skeletal muscle. So, activate a stress response, right? Increase our heart rate, beta 1. We're going to redirect some blood flow to the skeletal muscle through beta 2 activation, so we get more blood flow to the skeletal muscle. In beta 3s, let's go back to, we were using blue for stimulatory, so that's a stimulatory, and we're only going to talk about one place for this, and that's going to be adipose. And that's going to stimulate lipolysis. Remember I said that sympathetic activation is primarily catabolic, freeing up energy stores? There you go, there's one mechanism through the beta 3 receptor. So those are, yeah, that's good enough for adrenergic systems. Since we were talking about receptor types, I included this as a reminder. So if I say which receptor types are on the dendrites of the ganglionic cell in the sympathetic nervous system, well, you're going to tell me that those are cholinergic receptors and they're nicotinic. So let's talk about cholinergic receptor types too. This is really complex here. So cholinergic receptors. Well, there's nicotinic. Let's see if I included. Nope, I did not. Nicotinic receptors. Well, that's that ligand-gated sodium channel that we've been talking about. And it's literally named after nicotine, because nicotine binds those receptors and activates them. So I should use this so you don't confuse that. This is stimulatory, right? So this is a ligand-gated, I'm just going to say sodium channel. And our other type, muscarinic. Muscarinic cholinergic receptor. And it's usually inhibitory. There are a few examples where it isn't. Yeah, well, we're going to stick with inhibitory. Where is it found? In a variety of places. One of the places we care about, though, will be the heart. So parasympathetic input to some tissues, if it's a nicotinic receptor, it will be excitatory. But if it's using a muscarinic receptor, like on the heart, it would be inhibitory. Here's another example of the exact same chemical, acetylcholine, producing opposite effects depending on the receptor type that we're using. So again, pay attention to the receptor. The receptor is key to understanding how this works. And just the last couple of things, and I've already mentioned them, but they're very important, so I reminded myself here to make sure we talk about them, or at least I talk about them. Autonomic tone, it's a lot like muscle tone. So always basal activity. And like I mentioned before, just like muscle tone, if we cut the nerve, we'll initially lose some function there, but it'll be recovered by circulating catecholamines if it's in the sympathetic nervous system. Cholinergic system, you're kind of out of luck. You'll lose tone just like you would in the somatic nervous system, which is also using acetylcholine on its target tissue. In that case, they're always nicotinic also. So this tone's very important, especially if we only have one input, and I'm going to come back to that in just a second. I want to make sure we understand dual innervation. That just means both branches. Right, the parasympathetic. Put an S in there. Plus sympathetic nervous system. Right, those are just two branches of the same thing, and I described it as having like an accelerator and a brake. So we have this wide range of control. Now back to this tone. Well, not everything receives two inputs. Like there are some vascular beds that only receive input from the sympathetic nervous system. Having this tone is actually very important to maintain. Also, we still get a fairly wide range of control. Let me show you how that works. We'll use red to indicate a blood vessel. So we're looking at this in cross section here. So let's say that's fully dilated. This would be fully constricted all the way down here. So dilated there, constricted. I should probably use a different color. That's fully constricted. We'll use an example of a sympathetic nerve going to this that is going to be constricting. So this is going to cause vasoconstriction. I'm actually going to use blue to indicate about where that vessel is with this input. So we've got a synapse here, and this is from the sympathetic nervous system. So we're supplying some tone, we have some smooth muscle contracting, and this is where the vessel is based on the autonomic tone. So we always have some basal input going in here. Well, if we needed to fully constrict that vessel, we just increase the activity. If we want it to fully dilate, decrease the activity. And look at the distance it has to travel to get from to fully dilated to fully constricted. Now, what if we just did the opposite? We had no tone at all, so we were in this fully dilated state. And now we need to go to fully constricted. Well, it's a lot more distance to travel, isn't it? So it would take longer to produce that effect. And that's why I'm saying we still get a wide range of activity, even though we only have one branch of the autonomic nervous system innervating this vessel, because we stay in this middle point of partially constricted. So we can just either relax or constrict some more. And we have this wide range of activity that's very rapid. That's also why if you cut that nerve, we would get dilation out here. And that's why we saw that increased flow. Let's say this is, an alpha-1 receptor here in the skin. The blood vessels going to the skin. This is exactly what we'd see. And that's what we saw with that stellate gangliotomy that I showed you before. And that's just a very general overview of the autonomic nervous system with some of the key points. I'll fill in a lot more detail as we need it and talk about specific systems a little bit later on.